Okay, welcome. This brief video for statistics will cover how to run multiple regression in SPSS. So we've got some data here with where clients reported number of relapses. These are individuals struggling with substance abuse problems. And we've gathered a couple data on a couple of variables. We've got clinical judgment of depression, amount of daily stress, and then amount of social support and perception of social support. So one way to think about this would be, well, we've got kind of these two variables here, depression and stress, are, okay, indicators of pathology, and then amount of support and perceived social support are kind of strengths. So think about kind of risk factors and strengths. So we could group those together and try to predict, okay, when is a relapse going to happen? When you have a whole lot of risks or not enough strengths, or which one is a better predictor? So for regression, you should analyze regression linear. So the criterion variable you're predicting goes in the dependent box, right? Because criterion variables are analogous to dependent variables, and predictor variables are analogous to independent variables, even though because it's the correlation study, they're not true independent dependent variables, they're not IVs, DVs. They are analogous. The simplest way to run a regression, and this isn't necessarily the way you need to do it, would be to enter all these predictors in as independents all at once, right? And what that's going to do is, okay, they all go in on one step in one block together, and you're going to see, which one is the best predictor while considering the relationship each other one has with the criterion variable. We just want to specify what statistics we want. So we want the model fit, estimates, the R-squared change we'll typically ask for. It won't really matter too much for this because we only have one step, and descriptives. Okay, that's about all we need. Right now the method is enter. You can see there's also stepwise, remove, backward, and forward. We'll just leave it as enter, simplest one. Okay, and it comes up. Okay, we've got the means, so descriptive stats for these variables, which if you had to do a results write-up, you'd want to report the means and standard deviations for all the variables involved. You've got the bivariate correlation, so just the Pearson correlation coefficients calculated. So relapses didn't correlate very highly, it looks like, with depression, did correlate with stress, negatively correlated with amount of social support, and an even larger negative correlation with perceived social support. Then you can also look at the correlation among your predictors. And here's where you're looking to say, okay, I don't want any of these things to be too big. I don't want to see any, 0.8s, 0.9s among, like with depression, with stress, or social support, perceived social support, with actual social support. Because if I did, I'd have multicollinearity, and it's going to make my beta weights wonky. So those all look okay. Come down here to the model, and you can see you've got an R value, the R squared, which is literally just that 0.651 squared. Adjusted depends on which stat nerd you agree with, if you will report the adjusted or not. Most people just report the unadjusted R squared. There's the F value associated with it, 415 degrees of freedom, and significant at the 0.000, lots of zeros, all the way down to 4. So definitely a statistically significant model predicting relapse with all those predictors. Then we come down to see, well, which predictors are doing the heavy lifting here, and you can see some redundant information here. Degrees of freedom 415, there's the F again, there's the same sig. So an ANOVA is run on regression because they are, like I've said in class, mathematical cousins. But it's the same numbers you'll see here and here for the F change and the F. So the coefficients, you've got unstandardized coefficients with the beta, or the B weight and the standard error. Then you've got the standardized coefficients, which are betas, and then a t-test to determine if that beta weight is statistically significantly different from 0. So difference between B weights and beta weights. The B weights are, if you really wanted to write out the regression equation to predict, okay, what's my Y predicted based on different X values, these are the numbers you would use to put into the formula, right? So each one of those, you'd have 0.014 times what the depression score was, plus 0.292 times their stress score, minus 0.527 times their amount of social support score, minus 0.701 multiplied by their perceived social support score, right? And if you did all that, that would give you their predicted relapse. How is that different from the standardized coefficient beta? Well, the standardized these unstandardized coefficients, you can't really compare. You can't say, oh, this 0.701 is bigger than a 0.527, right? Because it depends on if the amount of social support and the perceived social support are measured on the same scale, right? If one of these is on a 10-point scale and the other is on a 3-point scale, okay, well, the highest value on one's a 3, the highest value on the other one's a 10. So when you're multiplying it by something, what you multiply it by to get your predicted y is going to depend in part on how big the score, how small the score can be. So the standardized coefficient betas are the ones we more often will look at and interpret, because just like z-scores, they've been standardized. So I can compare betas to each other. I can say, okay, yeah, the strongest predictor when they're all entered the model at once is perceived social support. 0.44 is bigger than 249 or 186 or 093. Okay, so the unstandardized ones you use if you actually wanted to write out the formula and use that to predict somebody's score, give it an x value. But we don't often do that. More often we want to know, well, just which one's the strongest predictor. And that's where when you look at the standardized coefficients beta. We also will report out which predictors contributed significantly to the model. So again, the t-test is run on the betas, and here's your p-values associated with those. So we see that the bottom three, stress, and then amount and perceived amount of social support, are all three significant predictors, and then clinicians' ratings of depression, not significantly predictive of relapse. Okay, so again, that's the simplest way to run it, but not necessarily the way you'll want to do it, because it's more interesting. Come back in here in regression, linear, to do it. Look at it a couple different ways. I mentioned in class stepwise regression, right? So stepwise regression is different from the inter method. Inter method, they all go in one single step. Stepwise says, all right, fight it out. Whoever accounts for the most variability, you get to go first in the model. And then after you've eaten all the variance in y and relapses you can account for, the next one gets to go in, and then the next one. And at some point, there may be a predictor that is, there's no unique variability left over for it to predict. And so it's eliminated. It's kind of kicked out of the model. So this is helpful often if you have a bunch of predictors, like, well, I've got these 10 predictors. I can't use them all. Some of them are probably redundant. Okay, so use stepwise regression to figure out, okay, which one or which ones are most important and unique, right? Because there may be, okay, I've got A, B, and C. B and C are both significant predictors of Y, but they both predict Y in the same way. Well, I don't need to use both of them then, right? I can just look at one of them. And then these other methods, remove, backward, and forward, are similar to stepwise. I won't go into details on that. Just they do it in a kind of a different order. But stepwise does with the, okay, first step, strongest predictor, and then the next one, the next one, the next one. So if we run it like this, we'll see the same correlations. We can see that we're now given 3 steps, right? So perceived social support was entered, and then added amount of social support, and then added stress. No mention of depression, you'll notice. So 3 different models now. So 3 different F's, right? So step 1, whenever perceived social support was entered, so that was the biggest 0 order correlation, right? We can go back up here, look at perceived social support with relapse. Yep, it was a 0.57. It was bigger than all the rest, so not surprising, it got to go first. So when it went first, it was significant all by itself with an F of 57.987. And then in step 2, when you added amount of social support, now we've got, okay, F changed. It went from 57 to about 67 something, right? So the F change of 9.7. So the first F was 57. F change meant it increased by this much, and that change was significant. So it added unique variability. And then in step 3, when we had stress, again, it added even more unique variability is being added each time. Well, originally we accounted for this R squared change, which is the same as R squared, 32.9% of the variability. Adding social support added a little bit, 0.05 or 5.2%, and then adding stress added another 3.5% of explained variability in number of relapses. Again, you see the same thing here, model 1, 2, and 3, so the 3 steps, their significance. And we look at the beta weights, and you'll get different beta weights depending on which variables are in the model. Right? So when perceived social support is in by itself, it's got this big old honking beta weight of 0.574, which of course is significant. When you add that in step 2, you've got perceived social support and the amount of social support. The beta weight for perceived comes down a bit, right? Because now it's having to fight with the amount of social support. Okay, this is only unique variability. Right? You got to go first, but now we're only going to get beta weights based on what we can predict, not counting for what the other one predicts. So the beta weight shrinks a little bit. They're both still significant. And then when you add in stress, it shrinks even more. Amount of social support, notice it doesn't shrink very much at all, 238 to 233, right? Which suggests that that stress variable is pretty unique from these social support variables, and all 3 are significant. You can see down here that depression is excluded. So when they're all in the model, it's not significant, so it's kicked out of these other models. Right? Okay. So that's stepwise regression. For your homework, you're going to do even a little differently, right? So let's reset all this stuff. So we've got relapses, the thing we're predicting. We want to look at kind of a hierarchical regression. We're looking at steps that we specify. And maybe you're curious if, okay, well, these kind of risk factors, are they adding to prediction above and beyond the protective factors, and vice versa? Are the protective factors adding above and beyond the risk factors? So we'll put in those factors that share a common theme in the same step. So we'll run the regression 2 ways. First, we'll run it with our risk factors, so depression and stress, move them over. They'll be in block 1. You see here we have block 1 of 1. If I just click next, that gives me another thing, and I can put in my risk factors. So my strengths, my protective factors, amount of social support, perceived social support, put those in. Okay, and I can go back here. There's block 1 of 1, and there's the second block. Even though it still says block 1 of 1, they are both there, no worries. And my stats should all still be selected. Model fit, R squared change, descriptives. Yep. Okay. I say okie dokie. Again, I get my bivariate correlations. It gives me p-values for all those. And again, I've got, okay, 2 models. Step 1, stress and depression entered. Step 2, amount and perceived amount of social support get added to the model. So when I have my risk factors, stress and depression, and by themselves, okay, I've got an R squared of 136, so 13.6% variability explained. The F change, 2 and 17, 117 degrees of freedom, is significant. When I add the other things, social support and perceived social support, the R squared goes from 136 to 424, which is a change of 0.404. So added a lot of explained variability, a 40% increase in the amount of variability I can explain in number of relapses when I add in those protective factors, and it is a significant addition to the model. Again, redundant information here in the ANOVA. I come down to the coefficients. So depression and stress, when by themselves, depression 0.047, that's pretty small, not a big surprise. It's not a significant predictor. So even though those protective factors together were significantly predicting relapses, depression wasn't doing anything. It wasn't contributing significantly anything unique beyond what stress was doing. Stress is doing all the heavy lifting with a beta of 0.36 and it being significant. So again, not too surprising. When everything's in the model, depression still not significant. And occasionally you will get this weird finding where something that's not significant in step 1 pops and becomes significant in step 2. And that's something that we can discuss if you take another advanced stat class. But generally, you won't see it. If it's not significant in step 1, it's not going to suddenly become significant in step 2. So depression is still not there. And now stress, the beta weight gets smaller, still significant. But then we look at the beta weights for amount and perceived social support, 249 and 440, both significant. So those seeming to be doing the most in the predicting, and which variable is the best predictor of relapses among our choices for protective factors? Well, that would be this perceived social support, and I look at this 0.44 to tell that 0.44 is bigger than 249. I don't look at the 701 versus 527. I don't look at the unstandardized coefficients. I look at the standardized coefficient betas. Okay, so that's how we ran it with, we put in the risk factors first, and we say, okay, well, how much does adding these protective factors, what does that do? I could also run it, regression, linear, the opposite way. Back those out. Okay. So now I'm going to put in my protective factors first, before I put in the risk factors first. Now, protective factors, you get to go in block 1, and then my risk factors, I'll put you in block 2, right? Because we found out that, oh, these protective factors, they really added a lot. Okay, well, how much are the risk factors adding? And this would be a way to answer that question. Okay, same correlations. We see the first model is significant. When we add the risk factors, it's still significant, but it's not a big change, right? F change of only 4. How much additional variability in relapses were explained when adding the risk factors of depression and stress? Well, we look at this R-squared change. Well, about 4.3%, right? So adding the protective factors adds a lot, adds 40%. Add the risk factors, only 4.3. So if you had to pick, okay, well, which one are you going to go with? Well, I'm probably going to go with the protective factors, right? They're doing more of the work. And again, we'll see that story play out here in the beta weights. When they're by themselves, both are significant predictors, with perceived social support being a stronger predictor. When everything's in the model, perceived social support is still the best predictor, amount the second best, and depression not contributing significantly, and stress a significant but minor contributor to the prediction of relapses. Let's see. All right, that's about everything you need to know for regression. As you'll see whenever you're reporting for APA style, you'll often want to grab the R square for the full model, maybe the R squared change if you're talking about a second step, and then the F in degrees of freedom, the significance, and then you report the beta weights and the p-value associated with those beta weights. That's all for now. Take care.